So this little video I'm doing at the moment to the class live is about meter loading and the importance of using the correct meter when we're measuring circuits which have got large value resistors in them. Now, this circuit I've got on the board has a 30 volt supply, and it has a 680,000 ohm resistor, 680,000 ohm resistor, and I've used two different meters when I've done the lab. I've used one which is a moving coil voltmeter, which has 20,000 ohms per volt, it says on the scale, and it's on the 30 volt range. So 30 volts times 20,000 ohms per volt works out to be an internal resistance of 600,000 ohms. Now if I put that 600,000 ohms across this resistor, when I'm trying to measure the voltage across this resistor, I'm actually changing the value of that resistor. It's no longer going to be a 680,000 ohm resistor. The internal resistance of the voltmeter in parallel with that is doing what I've drawn in the inset here, 600,000 ohms in parallel with 680,000 ohms, to give me a new equivalent resistance of just 318,000 ohms. And of course I've shown the maths how to do that there. That's jumping ahead just a little bit in what I'm teaching today, but nevertheless I hope you can understand that. Now, we also had a second meter which was a DMM, digital multimeter, and the digital multimeter we measured 14.5 volts, but with the moving coil voltmeter we measured down slightly less than 10 volts. Let's have a look at the maths and see if we can make the maths work out and see why we got the values that we got. I've done two scenarios here, case 1 and case 2, and in case 1 I've taken working with the DMM, the digital multimeter, 10 million ohms in parallel with 680,000 to give me an REQ of 637,000 ohms. And I've had to add that to the other 680,000 ohm resistor to get the total resistance, and then I've used the total resistance with the total voltage to get the total current. Then I've multiplied the total current by that new value of top resistor with the meter loading, that is with the digital multimeter in parallel with it. 14.51 volts, and that's exactly what we measured with the digital multimeter. We had the two 680,000 ohm resistors in the circuit, and we measured 14.5 volts across there, 14.5 volts across there. We had previously measured 30 volts across there. Kirchhoff's voltage law, which we already looked at earlier today, says the sum of the individual voltage drops has to add up to the supply voltage, but 14.5 and 14.5 only adds up to 29 volts. We lost a volt. Why did we lose a volt? Meter loading. The digital multimeter changed the value of the top resistor just a little bit. It made it into 637,000 ohms instead of 680,000 ohms to give us that half a volt of difference. Now case 2 is with the moving coil voltmeter, which has 20,000 ohms per volt, and it's on the 30 volt range. So in fact we saw before the maths, it brought it down to 318,000 ohms. I've got the new total resistance in the circuit by adding the second resistor to that, 998,000 ohms. I've worked out the total current in the circuit to be 30 microamps, and I've multiplied that by our new REQ to get just 9.56 volts DC. 9.6 volts, we've got less than 20 volts total voltage if we rely on the reading of that analog multimeter. Why? It's severely loading the circuit down. So when we saw in our notes that voltmeters have to have high resistance, this is the reason why. If the voltmeter resistance, internal resistance, R subscript I, is too small and it's reducing the value of the resistor that you're measuring, it's going to change the entire circuit parameters and give you the wrong circuit readings. That's a very, very important thing to understand with fault finding in electronics. meter loading. Always choose the correct meter. Now, in our notes that we're going through, and we've taken that small departure away from the notes to go ahead and do this, and we did the small lab on the side bench with this. So here's the circuit that we used with our two 680 ohm resistors connected in series. Just connecting the multimeter across the front of it now. The high Oki is measuring around about 9.7 volts DC, as you can see. And here we are connecting the DMM, the digital multimeter, the Digitech, across the same resistor to get 14.57 volts. So both of those voltages tally up pretty well with the theoretical results that we got. The second part says that when we're using a current meter, we have to use something which has got really small resistance. That's exactly the opposite to the voltmeter, where the voltmeter needs really high resistance. This one needs really small resistance, otherwise it's going to add resistance to the circuit when we use it. We don't want to add more resistance to the circuit, so in the circuit simulator, when you accepted the default conditions for the ammeter, I think it said it was about 1.5 micro ohms or 10 micro ohms or something like that. It was a super low value of resistance, which some of you sort of asked me about and said, what's this really weird value of low resistance? That's why it's so low. It's a current meter. Current meters, good ones, have to have super low resistance. Voltmeters have to have super high resistance. And I forget what the default value for the voltmeter was in Circuit Maker 2000. Perhaps it was 100 million ohms or something like that. Anyway, it had virtually no effect, a negligible effect on the circuit. Any questions about this so far? Pretty open? Yeah. Look, I think it's gone above and beyond where we're going today with learning a bit about meters, learning about electrical pressure, which is voltage, learning about flow and current in a circuit, learning about the opposition to the flow of current in a circuit. But at the end of the day, we're doing a unit which is called troubleshoot DC circuits. So we have to know the tools and how to use them to be able to effectively troubleshoot these circuits and get the right answers. Okay. Thank you, Greg.